Okay, we just talked about integration in physics and how we actually are adding together pieces of a puzzle. We're taking an object perhaps and we're adding together all the little pieces to figure out what we want. If we're trying to find mass, let me make this, I don't know, rubber duck. Okay. If we find the mass of every chunk there, I'll call that dm, and we add them all together, we get the total mass. Now the sum of those dm's, if we can write these down in equation form, we can really call this the integral across all dm's, okay, of all those differential masses. And in general, if we're doing this, maybe we have information about what the mass density is at a certain location. So we'd add up the density times the volume or the area or the length and write our differentiation in terms of that and do it over the entire size of that little rubber duck. Okay, let's do something a little tougher now. Everything else you could do pretty much without integration. This is going to be, you can still do this without integration, but I want to show it to you because it's a little tougher thing. I've got some bar, metal bar like this, okay? And it turns out it's a lot lighter here and heavier over here. It's denser. It's got a higher mass density is greater there than the mass density here. So here we can't just do that. Let's take the density and multiply it by the length and figure out the total mass. We can't do that anymore. And so that causes a little bit of a problem. And let me give you an equation. Let me think of, okay, let's say that we're going to call that 0. Let me redraw it down here. Okay, so here it is. And let's say it has a length L. It starts at 0. And let's say that the linear mass density, pretend this is one-dimensional there, is, let's say, 3 times x. Okay. Where x is this distance here. This is my x. So if I want to find out that, once again, what I want to do to find that total mass, total mass is going to be the integral over the entire, let me put over entire object, however you want to do that, of all the differential mass elements, of all the little dm's. Now, I drew it two-dimensional, but I really want you to think of this as a wire, as something where we don't have information about that. We have this is a linear mass density. So we know that any chunk like this, we can figure out what the mass is. We just take the width of it, that length, and multiply it by lambda. So once again, it's going to be length over, mass per unit length. Okay. Now once again, it's irregular. Okay, lambda equals 3x. And that's the problem. So we can't just take that 3x and do something with that. But what we can do is we can say we're going to take all the little dm's. I just colored in one of them. And if we sum all of those up, if I sum this one, it's got one mass. This one's going to have a very different mass, even though it's the same width. This one will have a much bigger mass. So we have to integrate. What that means, we have to add up all those dm's across the entire object. It makes sense since the density depends on x on this position, that we start at one spot on here and go to another spot. We treat them all. I want to say that slice is fundamentally different from that slice. So I'm going to add that slice, that slice, that slice, that slice. And so those dm's I can really define in terms of where they are in x. Okay, and so I'm going to call that a dl. Well, let's just call it a dx. Okay. And I'm going to take my x and I'm going to go from 0 to L. I hope you're seeing that. In previous ones I called it dl. This time I'm calling it dx. This is just terminology. So I'm going to take that dm and rewrite it in terms of that x. And I'm going to go from 0 to L again. I've been doing this over and over. Eventually we'll get to other geometries. It'll be a little relief. Okay, so the mass of this guy is going to equal dx times alpha. That ends up being, well, let's just write it down there. So this is going to be alpha times dx, and that also equals integral from 0 to L alpha. Oh, I'm sorry, I wanted to write 3x down there. Substitute this in for alpha. Alpha is just 3x times dx. Okay, I hope you recognize that this x dx, integral of x dx we can do. We've seen that before. So let me write that. I'm going to take the 3 out. It's a constant. Integral of a constant times some variable is just going to be the constant times the integral of the variable. So it's going to end up being 3 times the integral of 0 to L of x dx. Let me write over here, let me write up in this column, the little rule for that, x to the n plus 1, integral of that with respect to dx is going to be, sorry, I wrote that wrong, x to the n is going to be x to the n plus 1 over n plus 1. So the integral of x dx is going to be equal to, let's rewrite this, integral of x dx is going to be x to the 1 in this case, x squared over 2. 3x squared over 2. Evaluated again from 0 to L. I leave out my constants because I have a definite integral. Okay, so that's going to be 3L squared over 2 minus 3 times 0 squared over 2. And that just ends up being 3L squared over 2. So mass equals 3L squared over 2. So once again, the keys that we've got, we figure out the total mass, we use the differential elements for whatever we're looking for. Then we try to rewrite those in terms of other things. Here it takes a little bit of, it takes a lot of practice, frankly. I see that this depends on x. This mass density depends on x. So I'm going to integrate across x. I'm going to integrate across the length of that thing. I'm going to integrate from 0 to L. And that way I substitute my lambda, my mass, my differential mass element, I can rewrite as lambda times dx, lambda times the thickness there. And then we just do this standard integration. You'll notice that the actual math part of the integral is the easiest part of all of this. The hard part, the thing you got to get used to, is the thought of adding up lots of differential chunks and figuring out how to select the differential chunks. That's the challenge. That's kind of the art to this whole thing.